In an earlier video, we have introduced logical reasoning, and we said that consists of two main topics. One is the syntax, and the other is the semantics. And we started writing sentences to understand the language, so that we express propositional kind of logic, and looked at ways that we can actually make inferences. In an early video also, we've seen an algorithm called model checking and backtracking search on how we can make inferences using this type of approach. Here in this video, we will see the second approach that we call propositional logic theorem proving, where we use syntax alone to do inferences. So this is the second and final approach that we'll discuss in this series, and we will just need to introduce a couple of sort of inference rules. So we will not be evaluating models or constructing models, but we will be using a couple of things, a couple of tools available to us. The first one is effectively a table of logical equivalencies, and this is the table of logical equivalencies. So we will stop the video now and come back after we fix the table over here on this page. Also, we need a set of inference rules, and as such, we will list two inference rules that we'll be using. The first one is called modus ponens. And the rule is actually written as a kind of a fraction where the numerator is the premise and the denominator is the conclusion. And for the premise, we have, if we have an implication and also the validity of the sentence A, then we can conclude that beta is also true. And the second rule that we will be using is called end elimination. And similarly, it expresses a premise that every time that we have A and beta, we can conclude that that A is true. Okay. Of course, we can also conclude that beta is true, but I wrote it here as A with A. Okay. All right. So the application of this propositional kind of theorem proving approach that uses syntax alone will go as follows. So first of all, we have an example here we are going to show, and this example will demonstrate this. This is the example, a show. So these were basically the inference rules. Now the query comes, what we need to show the negative P12. This is again from the Gumbus world, and negative P21 is true. Okay, so this is basically what we need to show. All right, so we will be using the table that we have developed during an earlier video when we looked at the Gumbus world in detail. And during that so we had a knowledge base. This knowledge base consisted of a set of rules. And the rule that we are going to be using here is rule number 2. So let me go back to that and actually see how this table came to be developed. So we had this Gumbus world where we started writing this kind of rules, and we assumed some kind of initial rules. One of them was rule number 2 over here. Okay, so we will start from this rule that definitely is a rule that involves the propositional symbols that are going to be involved over there, and we can actually see that that's our starting point. Okay, so let's look at this. So starting at R2, which is B11, if and only if P12 or P21. Okay, so we look now at the how we can, starting from that kind of rule, how we can modify it gradually in order to reach a point where we have this sentence to be evaluated to true. So we will start from using the so-called biconditional elimination. So we'll be replacing this the biconditional with the equivalent over on the right hand side. So we will just do that. So we write that B11 implies P12 or P21 and P12 or P21 implies B11. Okay, and this is my R8 rule, which I can store in the database, in the knowledge base. I already started with a rule in the knowledge base. I'm adding this R8 in the knowledge base. And let me write down what thing I have used. I used the biconditional elimination. Okay, so now that I have reached this sentence over here, I will apply then now the first inference rule, which is the end elimination. So from end elimination, I can do that P12 or P21 implies B11, and this is from end elimination. Okay, this is now my rule R9, and it's evident how the end elimination got applied here. I have alpha plus alpha and beta implies alpha, so I have or beta, so I have selected beta here, and that is basically what I did, and that's basically it. Okay, and then we have we took now this sentence and we apply the so-called contraposition rule. So the contraposition rule, so basically the way to sort of work with proposition logic theorem proving is that you have to have some kind of experience by looking at some examples in your textbook and trying to understand, you know, where you are and get some experience of which one is the most reasonable rule to logical equivalence to replace your sentence at any moment in time to go gradually into that kind of solution. So the as I said, we will apply now the contraposition rule on this R9, and we'll arrive at the replace this with this. So negation of B11 implies negation of P12 or P21, and this is the rule R10, and we did contraposition. All right, and now we will apply modus ponens, where we have from another earlier rule that we had in the knowledge base. In the knowledge base, back when we were discussing the knowledge base, we had the rule R4. We did the model evaluation by using the first four rules. So one of the rules R4 is that there is no breeze in cell 1,1. Okay, so this rule R4 still is in our knowledge base, and we will use it now when we apply the so-called modus ponens inference rule. So from R10 and R4, we will arrive, and which is going to give us the rule 11, which I'm going to write that now, we have the negation of B11 implies negation of P12 or P21, comma, negation B11. The conclusion is the negation of P12 or P21. And so this was my conclusion, and therefore this, by again using the De Morgan rule, we can get the desired result, which is, so this was basically due to modus ponens. And finally, the conclusion, let me call the conclusion R12. The negation of P12 or P21 is, of course, replaced with negation of P12 or negation of P21, and which is basically the desired result using the De Morgan logical equivalence. Okay, and that's basically kind of reached this kind of point where we have proven that the query is true using a number of steps. And as I said, practice is everything in that, how to use this logical equivalence and the so-called inference rules in order to reach that same conclusion. Evidently, this is the by hand sort of demonstration of the topic of theorem proving. And in propositional logic, we have automatic theorem proving kind of algorithms that are slightly outside of the scope of this course, as we're trying to get into just the basics here. And there are certain tools that will actually do this for you. And the construction of this tool took a lot of time and effort to make them kind of efficient. So for all kind of practical problems, provided we understand, if you like, the basics, hopefully you'll be able to apply those tools in any time you have logical inference, just doing the syntax alone. So out of the two methods we have looked at, the second method, the theorem proving, is also the most practical.